Good morning, Dr. Ajit and participants. This is fourth day's first session of our faculty development program on CFD. And today we have a great person from industry, Dr. Ajit V. From Dassault Systems. And he did his BTech from Government Engineering College, Kannur, and MTech from College of Engineering, Trivandrum, and did his PhD in modeling, wave propagation in composites from Indian Institute of Science, Bangalore. And he worked as an assistant professor in VJCET, and currently from 2014, he has been working as a Simulia Technical Customer Support Manager, Mechanical Applications at Dassault Systems Private Limited. So, Dr. Ajit, please take over the session. Thank you.
Good morning to all. I think I am audible.
Yes.
Okay.
Yes.
Good morning to all. Yeah. First of all, thanks for giving me this opportunity to address such a prestigious audience. For me, it's after a long time I'm interacting with academic audience, maybe a big audience like this. So thanks for this opportunity. I went through the the topics of the presentation that happened a few days, like what is happening. Most of the things will be like introductory kind of lectures, and mine will be a slightly different. I think like I will try to share what we have in our industry based on what I can share. There are some limitations for us to share with public audience. So within my limit, I will try to share what is the trend in industry. Okay. So as the topic suggests, okay, I'll start with my topic. Okay, finite element analysis, industrial applications and current trends. Means I am addressing this like I am talking assuming that like most of you know the basic finite element, and my focus will be basically on industrial applications. Okay, so before one second. Yeah, before this is my agenda. Okay, first I will try to tell something about what we do in Dassault System Solutions Lab where I work. Okay, after that something about simulation, the current trends and challenges, some FEM basics, and actually requirements in the real world. And next about Simulia. Simulia is the brand in Dassault System where I work, and which concentrate mainly on simulation applications. Okay, so what we have. So basically almost all the, like for example, our competitors, the basic things, what is available, capabilities will be same. So I will talk based on what we have, so which will cover general trends in the industry. Okay, and some examples where which I can share. Okay, publicly share. So what I can share is only based on what we can show publicly. So I cannot show what I actually do. So bear with my slides, and like that's a limitation from our side. Sorry for that, but I will try to share whatever like general ideas and trends based on what I have. Okay. So basically, Dassault System Solutions Lab. Okay, this is a major player R&D lab of Dassault System. We have branches in Pune and Bangalore. Okay, So basically, the main significance about this Dassault systems, earlier it was called 3D PLM software solutions. And the significance of this lab is like we have developments in almost all the brands what we have Dassault system. Okay. So for example, I'm showing some brands like CATIA, SolidWorks, Simulia, Delmia, 3D Excite, and there are more brands, but that is not relevant to our topic now. Okay. For example, CATIA is for a modeling software, SolidWorks modeling and simulation, Simulia, of course, it's for simulation, and we have in Simulia different. The main focus here is on Simulia. So the products in Simulia are like Abacus, Effisafe, Tosca. So these are the different products. For example, Abacus is for common structural thermal type of analysis. Effisafe is mainly for durability kind of analysis. Tosca is for topology optimization kind of examples. Okay. Delmia is for manufacturing simulations, and 3D Excite is for a highly like competitive kind of visualizing the like virtual simulations and all. Okay, and we also have a service type of company. Okay, where we help the customer to implement using our softwares. Okay, and discover 3D experience. Okay, currently this is the major trend in the industry. The last one, the 3D experience. Okay, so the 3D experience platform concept, okay, that is the current trend in industry. What is that? Actually, uh, so for example, I told you about Abacus is for structural analysis, Effisafe is for durability analysis, Tosca is for topology optimization. Here, the problem is with the customer is that, like, for example, if they want to solve a structural analysis, they need separate software like license for Abacus, another for Effisafe for durability analysis. But this platform concept is like, okay, for example, if you have a design, okay, if you want to design some component, uh, like the starting from the project management itself, you can do it everything in the same platform. That is the 3D experience platform. And this individual softwares, what was available like Abacus, Effisafe, will be here. It will be a separate apps. Okay. For example, instead of Abacus, we have structural scenario creation app. For CATIA, we have some other modeling app. So, but everything under same platform. So the advantage is that earlier, for example, Abacus is mainly concentrating on a simulation kind of software. So modeling aspect, modeling features available in Abacus will not be that competent to CATIA. CATIA is exclusively for uh, modeling software. So here, when you have apps in a single platform, we have like best from all the earlier tools available. And another thing is that it can be managed in a single platform. Okay, for example, if you have a design requirement, we'll model it in uh, one modeling app. Okay, then after modeling, we will use some simulation apps for simulating, and based on the simulation results, we will check the durability analysis. Okay, what is the life predicted? And for example, or also we will do some optimization, and after that again we'll do the durability analysis. And if if it doesn't satisfy the design requirement, again we can change the parameters. So it can be done in a single platform. And another important aspect of this uh, platform concept is democratizing the solution. For example, here the idea is like earlier, like oh, those who are expert in simulation, okay, they may not be that expert in sometimes modeling. So the customer needs, okay, this software, and they should be able to run the simulation everything without much expertise. That is the expectation, like a spoon feeding kind of. So here the idea is like we among the industry we will recognize, okay, we will figure out, okay, what is the exact needs, what are the analysis in priority. We will try to solve, like demonstrate this at our end, and this solution itself we will solve it. Okay, so what is the advantage of that? Okay, if they want to change something, if they want to implement, they can use the same solution. If they want to change something, they need to only change the parameters and repeat the analysis at their end. So that is about democratizing solution and solving industrial. So that's about Dassault System Solutions Lab. Okay, so I am basically working as a customer support manager for Abacus and FeSafe products. Okay, uh, so this is about Dassault System Solutions Lab. Okay, so now we uh, go to a simulation. Like, what are the advantages or different aspects which is like, which makes us, okay, simulation is actually needed. Why we need actually simulation? We can still manage with the some of the cases we can still manage with the experimental setup or analytical solutions. But the advantage is that, like for example, a crash type of analysis, drop test, how will you do the actual testing? Like, you can do it, but for example, if you want to uh, uh, at the exact failure, when the failure happens, we need to study more, like how the parameter varies. It's not that it's not that easy with the experimental testing. So for that we need simulation. What is the advantage? We have flexibility. You can see flexibility of parametric studies. Can with different number of parameters, we can do n number of tests. Optimization. We have like tools like Tosca optimization. Tosca, that is especially for non-parametric type of optimization. What is it like? For example, for a component, when we actually design based on the design requirement, we may not. I will tell you in detail when the Tosca slide comes. But the topology optimization is like, we may not need that much material to maintain that strength. Okay, so some of the materials can be removed, still the stiffness can be maintained. So how will you find that optimized structure? So that's about the optimization. It's not easy with the experimental setup. For simulation, with simulation, it's flexible to do the optimization. And another thing is fatigue analysis. How will you do the fatigue analysis? So with simulation, the life prediction, those things are easy. Okay. Uh, Earlier, the fatigue analysis, the durability analysis was not that important. Like, means people were not aware of what is the impact of this durability analysis. But after some crashes, what happened in like industry, like aircraft, for example, one of the we can see in the public literature about a comet crash. That crash happened because of the stress concentration at the square. uh, they were using square window, and near to that one rivet were there. So crash happened due to the durability load. What is the cyclic load about in a aircraft? We have pressure during takeoff, then during fly, and then again landing, again takeoff. So this is one cycle. So after, like, the prediction was something 10,000 life, but before that it crashed. Maybe after 1,000 cycles, it crashed because of this uh, uh, stress concentration and durability, cyclic loading. So how to simulate this kind of analysis? So simulation helps to do such analysis. So as I mentioned, okay, sometimes it's expensive to, like, in such cases with experimental setup. But in simulation also, what is the challenge? Okay, challenge is mainly how will you solve it? Okay, we have a lot of equations. How will you solve it actually? And do we have the resources? And do you know the actual boundary conditions, loading, material properties? So these are the main challenges. But now there is no issue with the uh, resources. We have a lot of resources, computer resources, and also that is not a question here. Okay. So FEM addresses. So conventional FEM is the most popular method. Okay, in addressing these, like, for simulation of multiphysics problems. Most, like, FEM or its variations, some of the variations are still popular to address this challenge of simulation of structures or whatever. Like, we have simulations in different fields. Okay, so that's about simulation. Okay, so what is FEM? Of course, you may be hearing about FEM for last few days. I'm just touching the basics only. Okay, we have numeric. It's a numerical method actually. Okay, solving partial differential equation, uh, different, like, two or three space variables. We can have two-dimensional, three-dimensional, and idea is like basically it subdivides a large system into smaller elements which are connected through nodes. Okay, and we will have a basic equations of stiffness matrix, like Ku equal to F kind of equation, where K can be, it can be stiffness in structural analysis, conductivity in thermal analysis, U is a displacement, it can be temperature in thermal analysis, like that. Okay, so basically we from the partial differential equation we will make it algebraic, like, in system of equations. Another variant of the FEM is like uh, uh, spectral finite element method. Similar method, but we solve it in the frequency domain. But the concept of uh, element and then globally arranging it, everything will be same. Okay, so and the concept is like we will solve individually. For example, we have different. We can model structures using different elements like continuum elements. We have 3 degrees of freedom, like 3D shell elements, beam elements. So these are general types of elements available in almost all the softwares available. Okay, so, and the idea is like the complex structure, we model it using these elements, and individually solve the elements, and we have a global matrix by assembling this individual and then numerically solve it. So that's about FEM. Okay, so now we addressed, like, we talked about the need of simulation. Okay, why we need simulation, and we have a tool kind of FEM. Okay, for simulating. Okay, now what is the current trend, like what we actually need? Okay, in industry. Okay, now it's a time for transformation trends. Like, we have a lot of applications, like, for example, 3D printing. 3D printing is a currently, like, it became popular currently, because, like, it can print, like, it can manufacture some of the complex forms which are not possible in traditional conventional manufacturing techniques. But the problem, like, with 3D printing is like, when you have such a product from 3D printing, it can have residual stresses, or, excuse me, okay, uh, residual stresses. And another thing is like distortions that can happen after, like, during the process. So simulation helps to identify these residual stresses, and that's the simulation of 3D printing. Means that's advantage. Another is personalized healthcare. We have, like, for example, we used to develop living heart models, like, how a, like, healthy heart works. So that can be used as a, like, baseline for a, okay, this is a healthy model, and when something happens, like, how the heart behaves. So these are all like simulation or trend towards personalized healthcare. Okay, the idea is like even a doctor without engineering knowledge could handle it. So that's the democratization. Okay. And virtual reality. Okay. Now we need to like virtually like we need to visualize everything. Okay. So this 3D excite our brands and all will help to like for in such kind of things like virtual reality. Okay. Virtually model these things like simulation of a vehicle experience, those kind of aspects. Okay. And electric vehicles, now it's about clean energy, and also a lot of trends like needs are there in electric vehicles, smart devices, personal aircraft. Okay. It's a new concept like urban air mobility, like air taxi and all. So idea is like if you have a congested city, how to overcome these things. So so a lot of simulations are happening in this area. So these are the like current trends where simulations can be applied, and uh, this is based on what we like our company like what are the industries where we need like simulations where we used to apply. Of course, it's a transportation mobility. We you like a lot of simulations are happening like crash, like other many analysis, suspension, crankshaft analysis, a lot of things. Aerospace, like fuselage analysis, complete composite structures, uh, and maybe like uh, uh, fuselage, cabin comfort analysis. So there are certain analysis like we used to deliver for the customers in aerospace industry, marine and offshore. Of course, a lot of applications are there also. Like for example, how to even in oil and gas, how to lay a pipe. Okay, how the pipe interacts with the soil. So how can we like means what are the interactions? So these kind of applications are there, marine and offshore, oil and gas, and high tech industry. Like we used to get a lot of customer queries based on drop test. Like Apple is our customer, so while dropping, like whether the current uh, mobile cover is suitable enough to like protect the. So those kind of analysis, drop test. Another thing is like high tech in industrial equipments like tire analysis. Okay. uh, Tire, then in the excavator analysis. Okay, we used to do the complete durability analysis of the bucket of the excavator, or design the excavator. Like we have a we apply the loading, or what is the maximum design load, and then uh, find like what should be the design, like the stiffness or so those kind of uh, durability analysis for excavator and design kind of analysis we used to do. Okay, so and there are more industries like life science, as I mentioned, living heart model. So I have included only six, uh, which is relevant, like mainly. So I have included only these uh, yeah, to our slides. Okay, so as I mentioned, uh, simulation. Okay, so what is the actual uh, advantage? Okay, so in terms of increase, okay, design space exploration. So if you have a simulation based design, the good thing is that like we have a systematic approach, more systematic approach. So that that is very good. Like, and another thing is optimization. Okay, the scope of optimization. Optimization is like another thing is that confidence level. Okay, we can do the test like many times, like, and so it's not easy with the real experiment. So the confidence level will be high, and complexity in management. Like here, every like the platform concept, the idea is like manage the project in a single platform. So it's easy to manage the complexities. Another thing like cost. Okay, so cost can be reduced. Design like time to market, that can be reduced with the simulation. of course, failure and risk. So, this is these are the real values of simulation. Okay, mainly main values that is considered, as especially industries are concerned. Okay, mainly they need time to market, they need to reduce it, cost, reduce it, confidence level. So these are the major values of the simulation. Okay, so we have, sorry, so uh, we have talked about the need of simulation. Okay, some of the trends in industries. Okay, and some of the industry where simulation is actually used. Okay, and before that we also discussed about the basic FEM. So earlier I also had the similar issues. Like, okay, when we in academics, or when you actually learn FEM in a coursework, we will first talk about like some axial rod equations, like then beam, maybe maximum till plate. Okay, and mainly about like we talk about elastic. Okay, but the problem is like when you actually like want to do the simulations in the industries, what we discussed like in the previous slides, is it enough? That's the question. So I was like everything cannot be. I know that it's not easy to cover everything in the coursework. So, but what I can say is like, okay, the major thing like that, the most popular method, like the FEM or its variation, is still applicable to address all these challenges. But only thing is that we may need some more additions, or like some kind of applied kind of FEM. So that's the, but mainly that conventional FEM is still applicable. So what are these additions? What actually is needed in real world applications when you want to address these real world issues? What are the additional things what we need to be aware of? Okay, basically, like main thing what I want to tell is about the non-linearity. Okay, uh, it can be a material non-linearity. Okay, for example, if you want to have elastic plastic, hyperelastic, hyperelastic is mainly used like in tire kind of analysis. So how will you? So when you, if it is elastic, then it can still like the Ku equal to F can be solved easily. It's a linear solution. But once you have this material non-linearity, we need to have different kind of approaches. So material non-linearity is one complexity, which additional to the basic FEM thing, like geometric nonlinearity. Okay, if the like rotations and linear translations are more like it's that is geometric nonlinearity. Okay, so in for material nonlinearity, we can see, okay, the elastic plastic, it can be completely plastic, like different models are there, like we can model creep, whatever, like, so that should be addressed, like for addressing a real world problem, we should have a material nonlinearity model. Okay, another thing is geometric nonlinearity. The third one, that is a major like a component, that is modeling contact. You see here, it's a cantilever beam. If this is not there, it's a simple cantilever linear analysis. But once you have a contact, it's a different problem. That will introduce nonlinearity. So how will you? There are different methods to address like model contact in almost all the softwares. Similar, like it's a kind of constraint optimization. Can be Lagrange multiplier or penalty based methods. So uh, here in our like tools, what we use is like if you have a contact between two surfaces, we will model it as a slave and master, and the slave nodes to master node constraint, we will model it, define. We can, different methods are there. So that's about modeling contact. And frankly, I can tell that, okay, I belong to support, okay, in our company. Most of the customer queries to us is the convergence issue with contact, and like it's a very difficult topic to address. Like each problem will be a different, like we cannot generally give a guideline like in contact analysis, contact modeling. So it's a difficult topic. Another, okay, geometric nonlinearity we have discussed. Okay, so so another like nonlinearity is like, for example, if you have an unstable kind of structure, a buckling load, or like it's difficult to solve this. Like when you have a negative kind of stiffness, uh, it's difficult to solve. So we have separate methods like Rick's method. So idea is like we will like limit the uh, time increment, and based on the tangent. So we have certain methods to address how will you solve this area. This is very difficult with the common Newton-Raphson method solved. Okay, so we have separate methods. So that is about unstable, addressing instability. Okay, next one, substructures. Okay, substructures. What, like it's kind of super element concept. Like if you have a repetitive kind of components, for example, a turbine blade, or like we don't need to solve everything. Like uh, means we don't need to solve the complete 3D with every blade. The idea is like we solve one and store it as a element. Okay, we can call this substructure wherever needed. Okay, and only a few nodes that represent the complete metrics, like internal metrics, will be called, and that in that way you can reduce the size like anything. So that is about substructures. Submodeling is like, okay, we have a big, like for example, a complete fuselage analysis, but we don't need the complete analysis with refined mesh. Our focus is only a small area or something like that. Okay, for example, a particular stiffened structure, or so we can do the complete analysis with the Gaussian mesh and do the submodeling for that particular area where we need focus. So the thing is that the global, from the global analysis, we will have some representative nodes which contains the uh, which can be used for submodel analysis. So we don't need the whole uh, global results or global model for the submodel analysis, and you can do the uh, refined analysis. So that's about submodeling. And then crack. Okay, of course, we have extended FEM like with enriched solutions and all. And fatigue. Fatigue is like, as I mentioned, durability analysis is very important, especially in aircraft structures where we use composites and all. So durability analysis uh, is very important. The software should also include this fatigue capability, so that is expected from the customer. And CEL, of course, it's a coupled Eulerian Lagrange approach. For example, if you have like, normally Lagrange approach is the like is used in our FEM, but if you have excessive kind of material flow, we have methods kind of which can club this Eulerian and Lagrangian, especially wherever needed. So such kind of capabilities are there. Like, and DEM like discrete element methods, where like you cannot apply this continuum mechanics approach. This DEM methods are also needed. For example, in soil interaction, some of the cases we need this DEM kind of approach. Adaptive meshing, like adaptive meshing is like we have excessive distortion. We also use the capable the efficiency, like we use the flavor of this Eulerian method to address this uh, highly distorted elements. So that's these are some of the methods. And thermal structural analysis, like Sometimes they may need, like we may need sequential or coupled. Coupling is actually needed where high non-linearity is there, where we have a lot of means coupling effect is significant. We need to do like complete coupled thermal structural analysis. Otherwise, we can first do the uh, structural analysis and we can add the solutions to the means first do the thermal analysis and use these solutions for the further structural analysis. That is sequential kind of analysis. And thermal, electrical, electromagnetic. So, and SMG. SMG is like, for example, we don't need like to solve like all the 3D model. Like here, even if you have a lot of complexity, the idea is not to solve all the models with 3D, all the complexities, anisotropic. That's not idea. We can still use the engineering judgments. The key concept is like instead of solving all the 3D analysis together, we first solve the axisymmetric problem, and from that solution results, we will transfer the 3D results. Okay, so we don't need to solve all this 3D analysis. So that is about SMG. Subroutines. Okay, sometimes the material models or some of the elements available may not satisfy the customer requirement. So we should have an option. Okay, to add the customer requirement using some subroutines, visualizing results, and if you for some of the post-processing scripts that should be compatible to the softwares available. So they need a, if, for example, if the software doesn't supply a particular variable, customer should have an option. Okay, using script, they should be able to post-process and find that particular output. Okay, so such an option should be available. And another like major issues when you do a finite element analysis, like for example, right procedure type. Like for example, uh, decide okay whether it can be static type of analysis, dynamic. Okay, whether the inertia effect is like that is significant. So how to decide those things, that is very important. Another thing, another aspect is right mesh and right element. For example, if you are using a fully integrated continuum element for bending type of application, we will experience shear locking. So for that, we have like quadratic elements or reduced integration elements where this shear locking effect will not be there. Okay, so right mesh, right procedure type. Okay, so as I already mentioned, idea is not to simulate every problem with all the complexities, but can still use the engineering judgments. Okay, wherever 2D is sufficient, you can still use 2D. Axisymmetry is sufficient, you can still use that. Okay, so these are the few cases like which came to my mind. Okay, so when you want to address a real physical problems, multi-physics problems, so these are the some of the features which needs to be there in our code or software. Okay, whatever we use. Okay. So now I'm going like as I mentioned, Simulia is our main or brand which uh, works for the simulation applications. Okay, and uh, and what we have in like the products and the Simulia, a lot of products are there. Like I just included what is relevant to this talk. Okay, we have Abacus. Abacus is mainly for structural analysis or thermal type of analysis, thermostructural, thermoelectrical analysis. Eyesight simulation execution engine. Eyesight is generally for a parameter optimization problem. Parameter means uh, within, like we have an objective function, we have design variables, like we have an optimization, how to solve that optimization problem. So for that, we have this Eyesight. EFISAFE, that software basically for durability analysis. We have stress-based and strain-based algorithms, and we have weld capabilities and basic steps, what is required. for the customer. So that is available in FSAfe. Tosca is of course for like topology. It's a non-parametric kind of optimization. So that is this Tosca is for that. And we have another tool like SIMPAC. SIMPAC is for multi-body dynamics analysis, and another like CST. CST is for electromagnetic kind of like wave, like antenna analysis. So such kind of analysis we have CST, and Aqua for wave kind of analysis. So these are the basic capabilities of our Similia brand. Okay, to address this customer requirements. Okay, so what is the basic concept? Okay, you can see here. Okay, we have a CAD model, CATIA. For example, our brand is CATIA for modeling. So we have a CAD model from CATIA, and we use eyesight. Okay, why we are using eyesight? For optimizing the mesh. Okay, so we have an optimized mesh here, and this mesh now we can use. So here what I'm telling is like how this different brands in Simulia can be applied for a simulation based design. Okay, so here we have a CAD model and optimized mesh, which can be used in a multi-body dynamics. And from the multi-body dynamics, we will get the force history of this engine, that means cylinder. Okay, and this force history is applied to Abacus to solve structural analysis. And from that, we will get the stress or whatever, like stress or temperature, whatever is significant for our purpose. And based on these results, we will do the non-parametric kind of optimization. For example, can we reduce the weight or some of the materials? Is it possible? So that can be done in Tosca optimization. And after that, again, with this optimized structure, what about the durability? So we have FSA for that. And finally, we get the durability or life. And if it is within our design interest, that design got passed. Otherwise, again, we'll do the same thing with different parameters. So these are the these are how all the tools are linked. Or the basic goal is like simulation based design. Okay, so this slide is about that. Okay, so I will just go through like what are capabilities are there in individual tools like Abacus Standard. Abacus Standard like employs solution technology ideal for static and low speed dynamic events and highly accurate stress if that is needed, we will prefer like high accurate solutions. Abacus Standard example includes like sealing pressure in a all the sealing pressure gasket joint, steady state rolling of a tire, crack propagation composite airplane flag. Even like Abacus Standard analysis has like capabilities like frequency extraction, steady state, random response analysis, linear, non-linear, and coupled temperature displacement analysis. Okay, so these are the basic capabilities available in Abacus Standard. With this, like we can address most of the some of the customer requirements in the real world, and we have a lot of material models for elastic plastic, hyperelastic, so that can be also used, or damage initiation models. Okay, and damage propagation models. We have different models are there. And Abacus CAE is mainly for pre-processing, modeling, and post-processing, visualizing the results. Abacus Explicit uses this forward Euler kind of integration scheme. So basically, Abacus Explicit is used for means short duration kind of analysis, like manufacturing. If you want to model some of the rolling analysis or manufacturing techniques, so we use Abacus Explicit analysis. And this figure shown is for a wire crimping example, which may be used for some of the electrical wire installations and all. So this is a crimping kind of analysis that is done in Abacus Explicit. Drop test, of course, Abacus explicit kind of analysis is the like has some advantages over Abacus standard analysis. And another thing is that, like, for example, if you have a some analysis that can be done up to a level we can do in standard, and next we can like rest of the parts we can do in explicit. We have options to continue the analysis, like we start like results from standard that can be imported to explicit and continue the analysis. Such kind of capabilities, okay, that may be also important when you have like the standard softwares, FEM with like FEM softwares. That is about analysis continuation capability. For example, if you want to analyze like manufacturing, like the rolling kind of analysis, and finally we need to do the spring back kind of analysis, Abacus standard is the standard will be efficient. So first we will do the rolling in explicit and final spring back analysis in standard. So we used to like, for that we need that continuation capability. Okay, so that's about Abacus. Next is FESAFE and Tosca. So FESAFE, this FESAFE, so the basic idea is like FESAFE, we use FEM results from some of the standard software, like for example, it's compatible to Abacus, of course, and ANSYS and Astran. So if you have a stress results from these softwares, based on the nodal output, FESAFE will do the fatigue analysis based on the algorithms we use. Okay, FESAFE also has welding capability, and some of the major aspects, like for example, here you see this is a fatigue analysis of a suspension component. So what is the effect of this overload? Okay, this kind of overload can significantly impact the residual stresses or mean stresses that will affect. You can see here these two, the failure area is different, same, but when you have this kind of overloading, the failure area, so FESAFE can predict such residual stress effect. So it's a good software for durability analysis, and it also includes the weld fatigue analysis. Okay, so another thing is Tosca. Tosca, like you see, this component will satisfy the stiffness requirement, but we don't need actually this much material. So Tosca optimization, this is the component after Tosca optimization. So this component will also help, like will be satisfy the design requirements and all. So how will you reach to this level from this? So there are different methods like stiffness based, eigenfrequency based. It's a non-parametric kind of optimization tool. Okay, so Tosca is for this such kind of analysis. Okay, then, and it will also consider, okay, it will optimize the structure and also consider the fact that, okay, whether it can be manufactured. So that aspect is also there inbuilt in the software, Tosca software. So the last few slides we talked about the individual tools like Abacus, FESAFE, etc. So in the first slide, when I talked about the company, I talked about the 3D experience platform. Okay, so the current trend is like not individual softwares, like we have a platform. Okay, so what is this Compass? This is what is called Compass, like Compass. So here we have different example. This is different quadrants are there. Okay, and each of these quadrants, for example, this quadrant, this V plus R quadrant, contains all the simulation apps. Okay, this is for, and this one is for 3D modeling apps. And this quadrant is mainly for project management application. How will you collaborate socially? And this one, this this is for like of all the industrial solutions available that will be there as a knowledge base article or something, so they can use that and continue with the simulation. So same platform, everything together. And the idea is like, instead of giving license for abacus and individual software, here we can, it's a role. Okay, if you have a structural analyst role, we can do the minimum capability, we can solve minimum structural analysis capabilities. For example, FGA role is for durability, so then I can solve durability kind of analysis. So what are the options available? Okay, we have structural kind of analysis, multi-body dynamics, vibroacoustics, electromagnetics, fluids, of course, sorry, fluids, automation. Okay, optimization. Automation means that like parametric optimization and durability. So everything as different apps, and we'll sell the roles. Okay, for particular role, we can do particular type of analysis, and we can, so we can like design the things based on like our requirement, everything together. Like we can using this quadrant, we can manage the platform. Here we have like enough information about the capabilities, or how you actually like demonstrated examples and all are available here. This is simulation, this is about 3D modeling. So that's about this 3D experience platform concept. Okay, so with that, now what's the time now? Okay, so with that, like I will move to like, so what we talked about is, okay, uh, the current trends of simulation. Okay, current trends in industries like smart watches, 3D printing. So due to these transformational trends, we need a lot of emphasis on simulation. Okay, that means we need to supply, like we need to, the customer requirements is high, so simulation capabilities also needs to be enhanced, and the whole concept is also different. We need to democratize the simulation. Earlier it was like, okay, customer also should be like should have deep knowledge in some. Now currently that's not a trend. Okay, within like manual interference should be minimum. With minimum interference, they should be able to solve complex simulations. How it is possible? This platform kind of concept. Okay, so we are giving industry what that different solutions, what is applicable to them, and with that they can move ahead with the their like needs and all. So we have, earlier we have different tools to address this simulation based design like abacus, eyesight, Tosca, everything. Now everything in the platform, okay, as different apps, everything together. So so we have, so these are the things what we talked about till now. So next is like, I'm going to show a video where that Royal Enfield, one of our customer, it's a publicly available document, and how they used our simulations. Basically, here in the video, what is included is a sizing optimization. With that, they could reduce the size of the size of the piston, and accordingly the associated components. So that's about the next slide. It's a simulate. It's a video. Okay. Okay, so that's about the slide on Royal Enfield. Okay, so basically, as far as this talk is concerned, the major thing what I want to focus is, okay, they used Tosca optimization, okay, sizing optimization to reduce that cast piston size. Then the next thing is the durability. Okay, earlier it was like they were individually like like connecting rod life analysis, but here we have the flexible body analysis. That capability is also available. So everything together they could do that. So these are the advantages. Okay, basically, and you get an idea. Okay, how they actually use these simulations in real world. Okay, I hope. So next, so that's about the transportation industry. Okay, so next we will another major area is additive manufacturing. Okay, so as I mentioned, additive manufacturing, it's like we have like uh, using like it's a complete kind of like it's a current trend in the industry. Okay, where the materials are deposited, and so we have some heat source like laser kind of source and material. Different methods are there, like powder based or based on different techniques. The material will be added as a layer, and a final component is made. So the advantage of this 3D printing is like we can have complex shapes, but as I mentioned earlier, like we have issues like how to find the like there will be residual stresses, how to find those things. So simulation is for those aspects. Okay, find the residual stresses, and of course optimize or topologize parts. Okay, optimization helps virtually test complete manufacturing builds, so that's possible, and we can find the residual stresses, and of course the failure predictions. Okay, if you do like if you simulate the structure and with the residual stresses, everything, we will do the durability analysis, we can get the durability life of the parts, and post-processing effects like different results, it's possible here. Okay, so that's the another area like where simulation is applied, like additive manufacturing. Next one is like industrial equipment. Okay, of course, tire analysis is one of the major area uh, in industrial equipment is considered. We can have a lot of analysis like brake traction analysis. Uh, so many type of analysis is possible. Okay, so that's about tire engineering. Okay, another major area where like industrial equipment where we used to work is uh, excavator model design. Okay, uh, uh, recently we had some project for the idea is like we have a bucket of this excavator model. Okay, and a lot of weld joints are there. So with the design load, okay, we'll apply the design load in the bucket. With the design load, what about the life of the weld? So that was the project. Okay, so we could find like the life predicted like were similar to what they expected, like with that experimental test and all. So that is one application. Okay, so here we have applied this horizontal load, like when you start digging, how the load is applied. We applied the load here, and based on, we know the arm length and all, based on that we found the design load. Okay, we have applied those load here, and idea was like whether it that weld and the structure withstands this load. So that's about the project. Okay. Then so this is about industrial equipment. Uh, so another like major area like it's like battery research. So we have another brand called BioVia, where we do this. Uh, the chemistry, that inner site modeling capabilities can be used in. But in Simulia, what we use is basically like our structural simulation. When it actually works with the boundary conditions and loads, how the battery life, battery strength, okay, those kind of analysis we used to do. Even for like similar analysis we used to get for packaging goods, and like when they drop some packaged packed component, what will be the impact for the inner component. So such kind of analysis we used to like which customer used to do, and we used to get a lot of customer requests for those. And of course, what like as I mentioned earlier, drop test, used to get a lot of queries on like mobile cover modeling. Like, so when they drop the model, it means drop a component, what will be the impact on that mobile? So such kind of studies is another area of interest. And of course, like this 5G communication, I told you that we have electromagnetic simulation capabilities. That is, CST is the software for that, CST. So with that, we can like actually do the analysis of antenna, uh, that electromagnetic compatibility, electromagnetic interface regulations. Like, so we can digitally validate the design. Okay, so whether we have, you know, like whether the waves are like communication is proper, like whether there is any unwanted emissions, those kind of analysis can be done. That is also possible, okay, in CST. Okay, so okay. Another, like I didn't add that slide, like another major industrial application is from aerospace. Okay, aerospace, we have like fuselage analysis, complete composite analysis. Maybe we have like uh, uh, as I mentioned, 3D experience platform. The idea is like democratize the solution. That means like a spoon feeding. Okay, we give the industrial solution to them directly. So we have certain like IPs, industrial process experience. So there we, for example, one of the IP is cabin comfort IP. So those who are researching or designing this cabin, so for them that simulation, okay, we sell the solution of IP cabin comfort. So if they want to change something, it's easy for them to implement a simulation. That's the idea. Uh, so that's a good aerospace. So next, uh, okay, with that, I'll go to another. Next slide. That is also a simulation. That's a video. Uh, that's about like EV like that is electric vertical uh, takeoff and landing. So that's a new concept. Like the current concept, like recent concept, where that for urban mobility, can we have that air taxi, and also when you have this air taxi and all, the next thing is like, okay, the clean emissions. So then acoustic aspects, like you have more air taxis, like what about the acoustic emission, noise pollution? So for that we need a lot of simulation. So next slide is about that. And go to the next slide. Okay. Yeah. So before one second. Okay. Yeah. So you see that like a lot of applications, like it's not limited to structures or even you can see that like 3D experience city. So uh, we helped the Singapore like government to like plan the city, Singapore city. So we have city planning, like where the flat can be like built. So such kind of planning is also like it's possible like in the using this platform. So even Jaipur city, we have collaboration. So this urban mobility, what we saw that like that video is about like including everything, like it's a part of city planning. Okay, so then when you go specific to the simulation, okay, we have different like noise and CFD simulations. So it's a complete like it's not about specific engineering simulation or nothing, like it's a altogether solutions, like that's what customer needed. So it's a time for like we need to like we cannot say that okay, I am only expert in mechanical or like FEM. That's not a trend in industry. Uh, we should have a like willingness to like collaborate with like multi-physics, like for example thermoelectrical, thermomechanical, magnetic. So that's the current trend. And also we cannot say that okay, we have delivered our FEM, now it's the customer's duty to like duty to do whatever they want. They should be aware of what, but that's also not the like good idea nowadays. We need to help them, like that's why supporting everything is important. So, I mean, it's maintaining the relationship, like when you solve something, we should like we should like they should be in a position to like comfortable with our or whatever they use. Okay, so we need to that's the idea is like a lot of research things are needed, like how to do that actually. Okay, multi-physics, democratizing the solutions, like how to do that. So we need capabilities, like we need to have a willingness to update ourselves and like from what we learned. Okay, of course the starting point is our coursework, FEM, everything, but from that like we should also know about the like what we actually do or what we actually need. So that's the main point, what I want to emphasize. So with that, uh, thanks for listening to me. uh, I know, like basically, like means my expertise is basically like what from what I shown is in abacus, like structural analysis, abacus, FESAF, and also uh, if I couldn't answer any of your questions currently, you can like this is my email. I can like I'll try to answer those questions if not solved today. That's what I want to say. Okay, thanks. Now it's over to you, like Swaraj. Yeah.
Uh, Thank you, Ajit. Participants, please type your questions in chat box if you have any. അത് എൻ്റെ ഇല്ല. Okay, Aji, we have a couple of questions. First one is from Abubakar Karangal. Can you please explain what is shear locking?
Shear locking. Yeah. Shear locking is like, for example, if you have a, for example, bending dominated problem. Okay, if you have a bending dominated, that where the bending load is the dominant one. If you are using a continuum element, linear, fully integrated, that means we have 8 integration points. So and linear. Okay, so with this linearity, it's difficult to represent this bending characteristic. So it's not, it cannot be exactly. So this, when you use this linear fully integrated elements for bending dominant problems, it will not capture this bending effect. So what we have, like that other options is like quadratic. For example, if you have a quadratic interpolation, of course we can have that curvy nature. Otherwise, another option is we use reduced integration kind of elements, where we have instead of fully integrated points, we only have reduced kind of integration, where but for that we need additional things, like we have some issues called hourglassing, where bending is not at all considered. We need to give some extra stiffness and all. So that's what we do in our software. So that's about shear locking. So I hope I addressed your question.
Thank you, Ajit. Okay.
The next question is, what is the difference in SolidWorks and CATIA application wise? And can we use Abacus for fluid structure interaction?
Yeah, Abacus can be used for fluid structure interaction. That's possible. SolidWorks and CATIA. CATIA is mainly for modeling, and the simulation capabilities are not that compared to SolidWorks. Yeah, SolidWorks is also mainly for modeling, but some like not specifically, like some of the capabilities are not there in CATIA when you come to simulation side. So CATIA is mainly, like, for example, all the features, like that modeling features will be the prominent one in CATIA. Simulation features will not be that great. So that's what.
Okay, that question was from Jishan Ansari. The next question from Dr. Anand Solanki.
Yeah.
How we coupled the thermostructural problem?
How will you couple means, what's the question? Like we have like means in their code you are talking.
That's a typed question from a participant. So,
Okay. If you want more detail, like I don't, like I can talk later. Like basically we have two methods in Abacus. Okay, I mean, based on our structure, like our capability, I can talk. Like one method is like means if you have that coupling is not that, like for example, if thermal, like structural solution will, like thermal solution will have an impact on structural. Those kind of coupling is there. If it is significant, then we have some like methods, like coupled temperature displacement methods are there to solve those like complete fully coupled solutions. Otherwise, what we'll do is like we have we first solve that, like if the interaction is less, if you first solve that thermal and then use that in the structural simulation. If you want more details on like what like algorithms, then maybe you can contact me later also. Like I also need to like exact formula, but you can check with me later also. Okay.
okay.
For the current talk, it's not that possible to reveal more on that. That's also another issue.
Okay. One more question is, Dassault, do Dassault have any specific software for CFD?
CFD, so Abacus CFD is there. Abacus CFD is there. Definitely have CFD capabilities. And in the 3D experience, I show we have CFD. That app is there. Fluid, for Fluid, we have different app. But the Abacus CFD is there. We have.
Okay, participants, any other questions? Right.